presentation mode.
How's this?
That's perfect.
Okay. Okay, well, thanks so much. I'm Kingson Man. It's my first time at Alife, and I'm so glad to be here virtually. Thanks for this chance to tell you about our work. So the title is Truth or Consequences, Homeostatic Self-Regulation in Artificial Neural Networks. And here we'll explore the question of what happens when machines can be set up to possibly care about the information that they are processing. So in the first part of my talk, I'll briefly review our perspective paper, which was published late last year in Nature Machine Intelligence. And in it, we ask, how do feelings arise in nature? We try to make progress in understanding natural feeling by building synthetic models of the phenomenon in machines. So we will look more closely at each of these terms in the title of the paper: homeostasis, soft robotics, and feeling. So it's now the year 2020. Where's my robotic butler? Put differently, why are robots still so dumb? With all due respect to the RoboCop players, but actually there's a relation to the internal simulation I'll get to later. So it's not all bad news. But certainly today's cutting edge robots can do some neat things, but there's still a huge gulf between these specialist abilities and the grand vision of general purpose robots. What is the source of this disconnect between aspiration and reality? Our group's study of natural, as opposed to artificial intelligence, has led us to identify a possible gap in current approaches to robotics. In particular, we draw on a set of theoretical contributions that my co-author, Antonio Damasio, has made to the understanding of biological systems endowed with feelings. He has provided a rationale for the emergence of feelings from the physiology of life regulation. So feelings are intrinsically about something, making it possible for an organism to gravitate towards states of optimal life regulation, maintaining life and extending it into the future. How does the organism do this? Homeostasis describes the set of activities that living organisms undertake to maintain the physical conditions of their bodies within a narrow range needed for integrity and viability. Quoting Walter Kennan, a pioneer of this concept, somehow the unstable stuff out of which we are composed has learned the trick of maintaining stability. And it was shocking to us that no machines today implement the fundamental principles of homeostasis, although there have been a few suggestive attempts. We believe this shortcoming may be responsible for the huge gap between our aspirations for robots and the really quite pathetic reality. So many attempts have been made to build emotions, quote, into robots over the years. In living organisms, however, emotional behaviors are caused by events that carry important consequences for their well-being. Emotive robots imitate the behaviors, but without the consequences. They are not driven by self-concern or self-regulation. They're more like puppets pulled by strings of computer code. Our approach to building a machine with something akin to feeling derives from a rich history. Gray Walter's tortoises on the left, with their simple sensors and effectors, could display interesting behaviors. Breitenberg vehicles were mentioned as well earlier. And more recently, the Cyber Rodent project evolved neural networks to support mating and foraging behaviors. But the homeostatic-like features, if present, have been implemented from the outside in. Agents are instructed to maximize or keep within a set range arbitrary values. It's unappreciated by the robot itself that if these values veer to an extreme, then its own existence is jeopardized. So the emotions and values underlying behaviors were not directly relevant to the system itself. All robots of this class would then be described by the philosopher Hans Jonas as biologically indifferent. We point to two emerging technologies that might allow us to build a new class of homeostatic machines: soft robotics and deep neural networks for multisensory integration. First, why soft robotics? The majority of today's robots are constructed from materials of convenience. So consider the life of a boxy robot constructed of sheet metal. In general, the metal is so durable that its integrity can be safely assumed or ignored, really, in a normal usage. But this durability comes at a cost. An invulnerable material has nothing to say about its well-being. Soft robots, on the other hand, more readily enter into a graceful and a sensitive coupling with its environment. There are more and more interesting things that can go wrong with soft materials. Their softness holds a deep well of vulnerability for us to draw upon. Now, the past decade has witnessed the birth of soft materials and soft electronics, which can be embedded on flexible and stretchable substrates. The most recent iterations can even sense and localize damage to their own structures and self-repair under certain conditions. One implementation on the bottom right uses droplets of liquid metal suspended in a polymer. When the polymer ruptures, the metal droplets fuse together and create a conducting surface, indicating the extent and localization of the damage. The end game, of course, is something like the miraculous material known as biological skin. Consider how densely embedded it is with multiple varieties of sensors and effectors. It's composed of cells that keep themselves alive, but also register itch, pain, temperature, stretch, vibration, and so on. We rely on it for the critical function of keeping our insides on the inside. It's our boundary against the world, and yet, an ant's jaws can cut into it. I encourage you to check out the paper where there's much more detail on the ethical questions of this project, relation to reinforcement learning, and so on. But for now, I'd like to switch gears and tell you about our latest experiments implementing some of these principles in artificial neural networks. So what if you could set them up to be vulnerable to the environment and to the objects over which it computes? The idea here is to build a model of synaptic homeostasis. Neurons in the brain need to regulate their excitability. Excitotoxicity can lead to cell death, and that's a real danger when you consume certain drugs. So what if we can import this idea into artificial neural networks that recognize objects, but are also needy? They also depend on those objects for their continued integrity and functionality. Our simulated agents contain neural networks trained to recognize images from the MNIST dataset. Critically, following recognition of the object, the agent makes a decision to either take it or leave it. That is, it can choose to ingest and eat or reject the recognized digit. Now, we add a twist to make the network's decisions consequential to itself. The digits have effects on the nervous system of the agent, so there's no blood-brain barrier. The digits 0 through 4 have inhibitory effects. The digits 5 through 9, excitatory effects. So think of the numbers as either being GABA agonists or AMPA agonists. These drugs can affect various components of the neural network, but we'll look at just one specific part, the learning rate hyperparameter, which controls how impressionable the network is to feedback. Now, to behave adaptively, the agent has to answer a question akin to, how does this make me feel? We use a counterfactual decision process to answer the related question. How would my own functionality be affected by taking or leaving this object? Here's a connection to the internal simulations that Heinrich just presented earlier. The agent first gives its best guess at what the object is on the left side, and then decides what to do with it on the right side. So it makes two copies of the base network. In one simulation, the recognized digit is left alone, that's on the top right, and you keep the learning rate current, and you perform a weight update on copy A. In another simulation on the bottom right, the digit is ingested. If the digit was predicted to be 0 through 4, the learning rate is decreased. If it was predicted 5 through 9, learning rate is increased. Then a weight update is performed on this copy B. Now, the agent selects some digits from its memory of previously experienced digits and passes them through both of the networks. The network that is more accurate in classifying these digits will determine which action to take. Now, suppose the decision is made to ingest the digit and alter your own learning rate. Now, the base level neural network executes this decision. In its backward pass, its learning rate has changed based on the true label of the digit and not the predicted label. So if the true label here is actually 0, it will be a decrement in the learning rate. Now, it's critically, this incentivizes the network to predict correctly, because otherwise there's going to be a divergence between its subjective simulation of the digit's effects on the right and the objective effects of the digit on itself on the left. Now we'll add one final twist that we can call the vicissitudes of life. So as so often happens, the rules have a way of changing on you. On one day, you learn a mapping that the label 0 means these round squiggles. And then on another day, we randomly swap 2 of the mappings between the labels and the images. Label 0 now corresponds to these squiggles and label 9 to these. And to top it off, the images have different effects on your learning rate. So typically in machine learning, you estimate the probability of label Y given the data X. In this livelier, non-stationary environment, the distributions of the data, X, are changing given the label Y. Our hunch is that homeostatic self-tuning of the learning rate will allow a greater flexibility to tune oneself in accordance to changing circumstances. Now, here we see some results. When you swap the label once per epoch over 20 epochs, the validation accuracy is comparable between the 3 types of classifiers. The homeostat in red adaptively regulates its learning rate. The conventional classifier in green is not affected by the digits and holds its learning rate constant. And finally, the randomly regulating classifier in blue blindly chooses whether to take or leave the digit. Now, what if we make the task a little harder? We increase the rate of digit swapping from once per epoch, seen before, now to 10 times per epoch. And we see a decline in performance for the green constant learning rate classifier. Interestingly, the blindly choosing agent in blue performs quite well in comparison to the homeostatic agent in red. And again, we crank up the difficulty even more. Note the change in scale here. Validation accuracy goes from 0 to 1, and chance level is at 10% on the bottom. So at 100 swaps per epoch, the red homeostat handily outperforms the green constant agent. The blue random agent, after some difficulty in the first half of training, comes to match that of the red homeostat. Finally, at the far right, on the extreme of 500 swaps per epoch, that really comes down to 1 digit flip every 100 digit exposures. So you really hardly have any time to get your bearings again. All networks have a hard time learning. The green constant agent performs just above chance. The blue random agent shows a significant variability early on, but recovers quite well. And the red homeostatic agent maintains respectable performance throughout. So just to conclude, the physical vulnerability and needfulness drives the feeling process in living organisms. We believe that soft robotics are a promising material substrate for models of feeling in machines. Oops, there we go. And then when learning comes with consequences, exposing one's own thinking machinery may improve one's fluid intelligence. And lastly, I want to include a future step we might take is to improve that counterfactual decision process to become fully differentiable. As implemented currently, it's a separate subroutine that's kind of hard-coded in. We're exploring new architectures to just get a single backward pass to modify your behavior as well. And finally, I'd like to thank you for your attention and to Hart and Evan for his helpful suggestions. And I'd like to acknowledge your sponsors. I'm very happy to take questions, and I'll be on Slack for the next few hours too. Thanks so much.
Thank you. That was great. Questions?
So I've got a question.
Yes.
Well, thanks for the talk, Kingson.
Thanks, Manuel.
I'm sure this is probably gonna go, you know, I wouldn't like this to, let's say, to go too deep so that it becomes like a 1 hour, you know, sort of discussion, because I'd like to give other people like the opportunity to ask you something. But I was wondering, you did mention Jonas, I guess, like at some point during your work, who, you know, was one of the driving forces, like in trying to differentiate between intrinsic and observer dependent goals of a system. So I guess in the type of work that you are trying to, you know, to bring forward now, how would you say such a deep issue could be addressed? Like, when is it that it becomes meaningful to say that a neural network or a robot has a goal of its own in a way?
So I don't think, I'm sorry, I just ended my share. Is my screen still okay? I'm never quite sure. Okay.
Yeah.
The question, I think if we want to make a distinction between intrinsic goals versus given goals, I don't think there's necessarily a tension between the two. So I think we can build robots that truly have their own goals that just happen to be aligned with ours. And you know, it would be good if they were aligned with ours. But I don't think that robs the robot itself of the truthfulness of its own goal. I like to think of it as yoking a robot. You can get a cow to have a very beautiful life, much better than in the wild. It just happens to be plowing your fields for you as well. So the reason I bring up Jonas is I have to say also, I first came to his work through Frozen, Zimke's work, but I think his work best illustrates really a glaring problem, which is all of these so-called intentional designs really only reflect the creator's intention. There can be no intrinsic intention in so simple a machine as, say, a thermostat or any other. I wonder about the governor. I truly do. It's a fascinating exercise. But I don't see there the fundamental link to integrity, physical integrity. It has to bottom out at you know, the reality of, am I going to keep existing or not? And from there, I think we have enough ground to build any kind of you know, edifice upon.
So would it be fair to say that you know, the intrinsic, perhaps fundamental goal of a system is to preserve its own existence, like in more or less the same shape and form? Would you call that like the ultimate goal, such that, you know, even like engineer systems might be said to have a goal in a sense that they will persist?
I think in our universe, it's the mother of all goals. You play that game or you're not around for long. We can talk about evolution maybe favoring replicators over preserving the vehicle of the replicator. I don't fully subscribe to that. I don't think replication takes precedence over homeostasis, really. I think you have to keep yourself around long enough to replicate.
Thank you very much.
Thanks, Manuel.
I have a question, or is it okay if I go?
Yeah, go ahead.
Okay, so I wonder, well, first of all, I really like the presentation. I think
Sorry,
it's
I can't tell who I'm speaking with.
Oh, it's Arseni. Arseni, can you see me?
Arseni.
I'm without a camera, but
go ahead.
So yeah, I wonder, how can you define homeostatic effects that would be helpful if you're designing a system that is supposed to do something, right? So in your experiment, like if you take one object, it's going to be, let's say, you know, increasing the learning rate. If you take another object, it's going to be decreasing the learning rate, or maybe it's going to change the weight of the network. Maybe some objects, you know, deteriorate the weights in general, and the agent is dying in a way, or like forgetting what it known before. But how do we design the effects that would be helpful for the end goal task if we're thinking about some kind of application? So for example, if I want a robot to learn to pick up objects, what do you think could be a path to defining those effects so that they're conducive to that task?
So if we think about the MNIST example, It's just patently useful to us for the robot to label things correctly. If we talk about specific examples, like I don't know, picking up cans to recycle, or fighting fires, or I don't know. I think it's a much trickier question. So how do we align incentives correctly? You can design the physical substrate of the machine to be needy for exactly that thing you want it to do. If it's an oil skimmer on the ocean for oil spills, without oil, its joints don't lubricate. For example, it's a worthless example. But I think the principle there is to identify the weakness, or to engineer in the weakness that aligns its incentive with yours. It's trying to solve a problem that happens to be your own too.
I see. Thank you so much. I think a related question is, how do you think your approach would compare to that of, intermediate rewards, shaping rewards? Because in reinforcement learning, many works, they have to introduce those intermediate goals. And it seems like it's overlapping, even though it doesn't use this homeostatic machinery, but people try to add motivations to agents. So for example, if things are playing soccer, right? Like the first goal would be for an agent to stand up at all and maintain an average height of its joints to be above zero or something like that, because otherwise it cannot walk, etc. Right? So how do you think it compares,
So yeah, there's actually a very deep relationship to reinforcement learning, but I want to emphasize this is not identical to reinforcement learning. The paper goes into that, but we point to an example of good RL work on homeostatic principles is Gutkin and Karamati's Alife paper from 2 years or so ago. But RL, I think of as just like weaponized guess and check, weaponized trial and error. You can, give it a very low bar for the complex movement of taking a step, like getting up and then swinging a leg, and then, at each step you can reward it for different things, and you slowly build towards your goal. But these are your curricula that you're giving to the robot, right? You are designing a staged learning process. I like the almost self-tuning or self-supervised is a hot term, learning that can occur when if the robot doesn't learn to pick itself up and move, if it's just going to be crushed or whatever. So there is definitely a connection to reinforcement learning. There is a process of trial and error, but that is not all that's going on in homeostasis. It is actively falling apart as time goes on, and that is enough incentive to get it to try things.
All right, thanks so much, Kingson. I think we'll move on to our next speaker. I think Dave Matthews is on deck.
Hello, let me just